Hi everyone, thanks for having me. My name is Tomas Howson. I'm from the University of Adelaide, from way down in South Australia. And today I'd like to talk to you about a data set of CAN bus data that we've collected on a project in association with Defence Science Technology Group from Australia. Now I am from Australia, which means for me it's currently about 3:30 a.m. So if I say something that's a bit nonsense, I apologise. So I'd like to start by preaching to the choir for a little bit. I think we can all agree CAN buses are pretty important. They seem to underpin a plethora of control systems that are used around the world. Almost every car out on the road today has one in its guts. It underpins the NMER system, which we'll hear more about this afternoon, I believe. Multiple sensor systems rely on it. It is an architecture that is pretty important. And it seems to be that if you can access one of these systems, you tend to know almost everything that's going on in it, on the condition that you can interpret the data as it's being presented. And so an intruder with a physical access to one of these buses should be able to observe almost everything that's going on, and hopefully from, well, not hopefully from that, seems to be from that, reverse engineer what the system it's associated to, vehicle or whatever, was doing during that time. Now, there are levels of security against this. Obfuscation of that data, whether intentional or otherwise, seems to be a method of hiding that. It definitely was for myself starting out with this. But of course, reverse engineering techniques are getting better, and so the ability to bypass that seems to be improving. So just like a brief overview of the CAN protocol itself. I'm sure most people in here are quite familiar with it, but the key points I want to sort of point out about it are that it, compared to other protocols like TCP, the sort of protocols that are used by, say, IoT devices in particular, CAN is quite simple. The message format is primarily composed of elements like the ID and the data payload itself, and then certain other flags that are associated with the bus. But at the very least, if you know these two components, you can reconstruct the important components of the message. This is unlike TCP in that, where you have source, destination, port, a whole bunch of other information. Here, it's just these two components, really. Now, of course, other versions of CAN, like the extended frame format, CANFD, CANXL, they make these bigger, but it's really still this relationship. You've got the ID and the payload. But that's, of course, where the specification ends. From there on, it's really up to a manufacturer, the OEM, on how they want to implement the protocol. And so the identification between a given ID and what that physical domain it's representing, the sensor it's related to, is entirely OEM dependent. The format of how they've chosen to represent that data is up to them. Of course, data types, precision, scale offset, all this sorts of information are entirely up to the manufacturer. Like here's an example, you could take the same information, encode it in two different ways, and if you take these heat maps as the binary representation, the same data can appear in a variety of different ways. So this is obviously a technique to hide the data, but I mean, we don't want to rely on that. But the question now is, say, if you had physical access to a bus, what sort of information could you get at, supposing you knew how to reconstruct this data in a generalized setting? So this is the title page from our submission. And I want to point out the fact that 3 of the authors, myself included, are from the School of Physics, Chemistry and Earth Science. I'm a physicist by training, so I was quite new to this field not that long ago. And so coming into this space, we had a few questions, like on the standard implementation of how CAN would appear in a real applied setting. Questions like, when you store an integer in CAN, how do you usually do it? 8, 12, 16, 64 bits? The question isn't how could you do it, but how do manufacturers typically do it? Steering wheel angle, is it usually a signed integer with 0 straight and positive and negative for each direction? Or is it usually 0 when you've turned the wheel all the way one way and then max value when you turn it the other? When you store a temperature, is it usually in degrees, tenths of degrees, Celsius, Fahrenheit? Yeah, turn signals, I mean, surely it's going to be left and right given a particular endianness. But then, of course, that raises the question of endianness. Do most manufacturers stick with a typical version, or is everyone mixing it up as they go along? I mean, given a certain type of sensor, is it going to be emitting at a certain fixed rate? Do all sensors emit at the same rate? Probably not. If it's, do some sensors only send CAN messages at an event base, you know, waiting for a request for information before they send? These are all questions that, fresh to the field, I mean, what do manufacturers usually do when they're implementing CAN? And the answer to all of these questions is maybe, if they want to. I mean, some might choose to do this. So the only way to answer any of these questions is to go out and get some data. There are plenty of great CAN bus data sets out there. I mean, it doesn't take very much Googling to come upon most of these. This is only a small sample. I mean, we could go and find plenty more. But in answering these questions that we had a few particular features in mind that we wanted some data to have. Very particularly, I mean, we wanted to see what cars are actually doing, so it had to be real cars to start off with. It had to be, well, we really wanted to see how CAN itself is usually implemented, so we wanted the raw packets, not necessarily it post-processed. We wanted to see a few different cars. Now, a lot of these data sets are particularly focused on intrusion detection, and so they'll focus on one car and show a plethora of different attacks, and that's great for that setting. But in this case, we wanted to see a few different vehicles, especially across different manufacturers. And we wanted some really granular information about what the bus is actually, or what the vehicle is actually doing during our capturing process. So we wanted GPS information, annotations on what the driver or the operator was doing. And so we decided to go out and collect our own data. And this is what I want to show to you all today. We've called it the CANdid dataset. It's not a CAN bus dataset without a pun on CAN in the name. So for this dataset, we've collected from a total of 10 individual vehicles, focusing on 4 separate manufacturers, going from about 2012 to 2018. So these are slightly older cars at the moment, now, but I mean, there's still plenty of these vehicles out on the road. So the idea of, I mean, this is definitely still applicable information. But of course, the important point about this is that we've also collected, along with the captures, video footage of the driver and the instrument cluster during capture, as well as GPS information from the drive. So from this, we have some pretty granular information about what the car did throughout the capture process. The actual device we used to collect the information is something I cobbled together out of a Raspberry Pi, and then the PyCan FD CAN bus interface. I plugged in through the OBD port. And then we also featured we also used 2 USB cameras to capture the video footage, as well as the GPS receiver mounted to the roof. The whole point of this is that we were using people's personal vehicles, and so we wanted a device that was portable, something we could install and remove on a vehicle without leaving any marks. People don't get too happy when you start trying to mess with someone's car. So we had a few conflicting requirements of this device. We wanted it to be small and maneuverable, but also enough to collect the data. I mean, there was some limitations to this. So the data we actually collected, we wanted to focus on 2 scenarios in particular for each car. We wanted both actual driving on real roads and real traffic. So we focused on vehicles driving on both main roads at 40, 50 miles an hour on dual carriageways, but then also driving around suburban back streets, so quick twists and turns, roundabouts. I don't know if you have many of those here. The whole point is that we wanted to record GPS information throughout that journey. That way we could pretty well reconstruct the path that the vehicle took along the drive. Now, because these were personal vehicles, there were limitations on our ability to use them, and so we weren't able to get the same path for every vehicle, but by focusing on these key features, we've got broadly similar drives for each car. But also importantly for us, we wanted to be able to isolate certain user components, to be able to reverse engineer pretty easily these particular components so that we could match them throughout the different vehicles. So we captured these, what we call control captures. It's almost like a Guitar Hero. The device tells you what move to make at certain times, turn the wheel all this way, turn the indicator on and off, and then we're able to take those captures with the device-generated timestamps, and then from that we're able to produce labels that very clearly match user actions with the CAN bus traffic from the vehicle at that time. Just showing that sort of in practice. This is an extremely simple statistical analysis, just looking for a correlation between the labels generated and CAN bus traffic, separating out each different CAN ID. And you can see that bright spot there shows, oh, well, that's almost certainly the ID that corresponded to the action we were looking for with this example. And so from that, we can just write a simple Python script to isolate out each of the components, and then from that, we're able to now compare across the different vehicles. So just to briefly show some of the sort of interesting points, well, at least I thought interesting from this. So looking at like the turn signals, the indicators, at least with this example here, for the given endianness we've chosen to represent it here, it does seem to be left and right. What's interesting is that the same data seems to appear in two different locations. Now, whether that's due to different sensors, different reasons, of course, it's difficult to say without actually behind-the-scenes OEM knowledge. But at the very least, yeah, this shows we're able to isolate it here. And so in this example, we've seen it formatted in this ordering. Then on another vehicle, we saw it in the other ordering. So, okay, there's not going to be any consistency there. Seems as though different manufacturers are choosing different endianness. All right, we'll have to keep that in mind going forward. Looking at the steering wheel angles. So in this vehicle, we were able to locate the steering wheel angles and show that it's being stored as a 16-bit integer. That sounds nice to me. That's a pretty reasonable format to store it. So it's a signed integer, so 0 being straight. On another vehicle, it was a 12-bit signed integer. Okay, so there's going to be some differences there. Going to have to keep that in mind. But 12 bits, still a pretty sensible number. On another vehicle, it was a 17-bit signed integer. I'm not really happy with that at all. Seems a strange number to choose, but maybe there's a reason for that bit up there being a separate flag for something. I don't know. So that's just some of the sort of, from this data set, we're able to say, okay, that's some of the differences you're going to see across the different vehicles. We'll have to keep that in mind. So now to just look at, okay, with the data that we have available to us, say someone didn't really know much about how CAN is implemented across different vehicles, could we perform a fairly simple analysis to try and just from the raw data packets without any knowledge of how CAN was implemented on this given vehicle, perform something like turn identification or any sort of maneuver identification. In this case, we want to identify, can we pick out when the car is turning without any knowledge of how CAN was actually implemented on this vehicle? So we've constructed input features by taking each separate CAN ID and taking their previous 100 or so messages and then forming a 2D image out of that. And then we've used the GPS information to construct labels of whether the vehicle was turning or not. In theory, you wouldn't have to use the GPS. You could find some other means, like following the vehicle and using a stopwatch or some other way to construct these labels. And then just two very simple machine learning models. These were able to be trained on a laptop, so really not that much sophistication going on here. This is just a simple feed-forward neural net, takes each image, flattens it, passes it through some dense layers, and then this is a convolutional neural net, so treating each image as just that, an image, and then performing convolutional, passing it through filters, and then through a final layer. And we can see in these cases, both models seem to perform quite well. You get an area under the ROC curve of above 0.9, which means, it's difficult to just look at that and say a number, but yeah, look at that number and say, oh, it's doing well. But at the very least, based on some naive interpretations of machine learning, you can say, all right, these seem to be performing or identifying when the vehicle is turning without any information from the analyst about what CAN ID represents what component. Now, from that, you wouldn't really have, just from that information, you wouldn't really have much in the way of, say, GPS information, but you could perform a timing-based analysis. So you could take the model confidence over time, look for peaks in that, and use that to identify a significant turning maneuver, which you might identify as turning at an intersection. And so mapping that onto some map information might be a bit hard to see at the back, but at the very least, there are peaks at each of the intersections on this road. And so from that, if you were a bit more sophisticated about your ability to time out how long it takes to travel down a certain road, just from this information, we could say, all right, the vehicle probably turned here, 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 and here. And so now you have a means of following the vehicle or reconstructing the path of the vehicle based only on its CAN data without any knowledge of how to actually infer that data. Now, just as a quick preview of where we're hoping to take this data set next, we've managed to pull out the engine speed and temperature. Not necessarily sure whether it's an oil or a coolant temperature because we're not entirely sure of scales and offsets, so we don't have much of information on actual values to map that to. But at the very least, we have these components, and so now we're looking forward to, taking a model that's able to take this identification on one set of vehicles and then agnostically identify this information on another vehicle for some, vehicle agnostic component identification. So just to summarize, this data set we're showing off here has data from CAN data from 10 different vehicles under typical operating conditions. with these special captures along with them to be able to help identify certain components quickly and easily. We've also included GPS data and video and annotations of the user's actions at certain times. And with that, we've been able to quickly identify components across a few different vehicles. And so, I mean, this is usually the point where we open up to questions, but I also have a question for all of you. If one were to go about collecting more data in this form, what sort of features might you find useful for this kind of analysis? What should maybe an analyst consider collecting alongside this sort of thing? But thank you.